Hey, welcome to our last lecture for the week. We're going to look at bond energies and calculating heats of reaction, which is kind of a sloppy way to write delta H of reaction, it turns out. And we're going to look at bond energies. And the thing about bonds is that when you break a bond, it actually costs energy. So when I go ahead and I break a bond between two atoms, say X and Y, those aren't real atoms, by the way, but breaking bonds costs energy. So that is to say, I've got to put in energy. A lot of people think bonds are kind of like eggs, and as you crack them open, you get energy coming out, but you actually have to put energy in to break bonds. That's what flames do. So when you burn something, actually the heat from the flame breaks all the bonds in the substance. Now, once you've got two atoms and you actually bring them together and they make a brand new bond, so once you make a bond, then making bonds, so I'll write a little arrow there to show, woo, we made a new bond. Making bonds actually releases energy. That is to say, it's exothermic. It gives off energy. It gives off heat. So when we make strong bonds, right, we release a lot of energy. When things explode, one of the reasons they explode is that explosives often have nitrogen atoms inside, and the nitrogen atoms, right, when you get them hot and they break apart, they can find each other and they can make that whopping great big triple bond there. And that triple bond is incredibly stable. In fact, you get 946 kilojoules every time you make a mole of this bond. So explosives often work, and they take these wimpy little bonds that have nitrogen bonded to carbon, and they break them down, which costs some energy, but you replace them with nitrogen-nitrogen triple bonds, which gives off a crap ton of energy. So that's kind of the name of the game if you're looking at explosives. So how do we use that to predict delta H of reaction? So it turns out we can go ahead and we can say, well, delta H of reaction, we can think of it as basically a two-step process. We have to break a bunch of bonds. So we have to imagine a reaction where we break bonds, and that puts in energy. And then as soon as we go ahead and break the bonds, we can make new bonds. And so when we make bonds, then that's going to give us a bunch of energy. So we can take these bond energies. I haven't shown you the bond energies yet, but I'll show you on the next slide. And you can look at how much energy it takes to break a bond and how much energy it takes to make a bond. And you just make sure it's positive for breaking and negative for making. And you put those two together and you can calculate delta H of reaction. All right, let's have a go. All right, so here's a table I quickly sketched out here. So these are 5 different bonds, and the amount of energy it takes either to break them or the amount of energy you get out when you make them. And let's have a look here. So the single bond versus the double bond. We said earlier the double bond is stronger, and we can see you have to put in almost twice as much energy to break the double bond. And conversely, when you make a double bond, you actually get almost twice as much energy than if you make just a single bond. And if you look at nitrogen-nitrogen triple bond, right, it is massive, right? It's almost triple the amount of energy you get from a single CC bond. And here's some other bonds down here. So let's go ahead and take a chemical reaction. So what's a great chemical reaction here? How about making some ammonia? So nitrogen plus hydrogen goes to make ammonia. And we can go ahead and we can say that delta H of reaction is basically equal to the sum of all the bonds broken. Right, that's going to be positive. And then we're going to flip the sign, right, and it's going to be the negative of all the bonds made. So bonds formed. So I got to draw Lewis structures here. So if I look at the bonds broken, so I've got a nitrogen-nitrogen triple bond, and I've got a hydrogen-hydrogen bond. In fact, I've got 3 of them, so I'm going to go ahead and do 3. And then, let's do these in blue. So on the other side, right, what kind of equation is this, right? So NH3. On the other side, I'm making 2 ammonia, so let's draw those in blue. So it's got N with 3 H's around it. So again, I'm kind of doing the Lewis structure part in my head, and the lone pair really doesn't matter for the bond energy, but it makes me feel better to draw it in, to be honest. So it looks something like that. So what I have to do, I got to break this sucker, this sucker, this sucker, and this sucker. And on the other side, right, I am making this sucker, this one, this one, this one, this one, and this one. Okay, so I'm going to calculate delta H And it's actually an approximation. So the bond energies are actually just averages of all the bonds. So there's actually lots of different compounds with an NH bond in. And so we've just kind of taken the average here and averaged it out to 389. So why might you do this? Well, if you don't know the heats of formation of something, you can't specifically calculate it. So if you know the bond energies, it just gives you an approximate way to do it. So I'm going to take my bonds broken. So I've got an N, and I got 3 HHs, and I'm going to subtract away from that 6 NHs. All right, so what do I have here? I got an NN, so that's 946. I'm going to be sloppy and leave all the units off to the end, so I'm sorry. Don't ever do this, by the way. So there we go. And we got 6 NHs, so that's 6 times by 389. And let's see, so this is a chemical reaction, so it's going to have units of kilojoules. And if we just go ahead and we add all this up, I get minus 80 kilojoules. So it is an exothermic reaction. Actually, experimentally, it's supposed to be about minus 92 kilojoules. So we can see it's pretty close, right? I mean, it's 13% error here. So whenever we got heats of formation, right, these suckers here, right, it's always better to use these and calculate them. But if you don't have them, right, you can just estimate them using this tricky kind of method.